Today we're talking about infinite geometric series. Infinite geometric series. And we're going to start off with a great story about Zeno of Elea. So Zeno had many paradoxes, and I think throughout a lot of his life he tried to prove motion was impossible. But anyway, let's go over one of his paradoxes here. Let's say Zeno needs to get to his work table over here, and let's call the distance between them 1 unit. Zeno says that this is not possible. He can never get to the table. And here's his reasoning. He says in order to reach the table, he must first cover half the distance between himself and the table. Upon arriving halfway, he would then need to cover half the remaining distance, or 1/4 total. Upon reaching there, he would need to cover half the remaining distance of that, and half the remaining distance of that, and half the remaining distance of that, and so on and so forth. And you can see that we're going to have an infinite number of halves, and therefore he can never reach the table. Now, if you were to add up all of these distances, 1/2 plus 1/4 plus 1/8, to try to figure out the total distance covered, plus ... and we let this go to infinity. You can tell that here you might even notice that our R value, this is geometric, and they're multiplying by 1/2 each time. And we're trying to add this up, but instead of adding up 10 terms or 20 terms, we want to go to infinity. Well, again, we can look back at our formula that allowed us to find the sum of n terms. But now the question is, what happens when n goes to infinity? So you might already know that when R here, and I think we established R is 1/2 for this series, we're multiplying by 1/2 over and over again, that when R is a fraction less than 1, specifically if its absolute value is less than 1, that this value, think about a fraction as the denominator gets bigger and bigger, like 1/2 is 0.5, 1/4 is 0.25, right, 1/8, etc. So our value of our fraction is getting smaller and smaller and smaller. So as this value R is raised to the n power, our fraction, if it's something like 1/2, to the second power would be 1/4, to the third power would be 1/8, to the fourth. As this power keeps getting bigger and bigger and bigger, the value of this term gets smaller and smaller and smaller. And in fact, at infinity, as n approaches infinity, R to the n, the term in the top here, becomes so small, it equals 0. At infinity, that value is so infinitesimally small, it equals 0. Okay, so if R is a value that's less than 1, if its absolute value is less than 1, as n goes to infinity, this term becomes 0. So now we would say that our infinite sum, if we looked at this, is the first term times 1 minus 0, because this term goes to 0, over 1 minus r. Well, 1 minus 0 is 1. And this a sub 1, if we put this over 1, we could multiply the top by it. So we'd have the first term times 1, which is just the first term, over, and in the bottom, 1 times 1 minus r is 1 minus r. This is the formula that if R, its absolute value, is less than 1, the infinite sum can be found with this formula. So let's use our brand new formula here and find the summation for Zeno. So if we plugged in our first term, which would be 1/2, and divide it by, so this is the infinite sum here, 1 minus our common ratio, which is 1/2. Well, in the bottom, we're going to need a common denominator. So let's make 1 2/2. And 2/2 minus 1/2 is 1/2. Oops. So we end up with 1/2 divided by 1/2. And remember, when you're dividing by a fraction, you would multiply by its reciprocal. Of course, you might note that anything divided by itself is going to give us the same result. It equals 1. But if we multiply by the reciprocal, we get 2 over 2, which equals 1. At infinity, this sum equals exactly 1. In fact, if you check that in a calculator and you just keep adding closer and closer values or smaller and smaller values, you get closer to 0.9999999 repeating forever, which at infinity equals 1. So here's the formula we just came up with. Zeno did not know this formula in his lifetime. He lived way, way, way back in the day. He was an ancient Greek. But now we know what happens at infinity. So this is the formula for any converging infinite geometric series, where this is the infinite sum, the first term, and the common ratio. However, it only converges if and only if the absolute value of r is less than 1. These values need to be getting smaller and smaller and smaller. We need to be adding smaller and smaller values, I should say. Okay, otherwise, the series diverges. So we need to do this check. If and only if it passes that check, we'll use this formula. Okay, determine if each infinite geometric series converges or diverges. Then find the infinite sum. So let's take a look at number 1. And they give us a few terms here. Let's figure out r. We need to find r. And remember, r is equal to any term. I'm going to pick 15 here, divided by the previous term, which is 45. And if we reduce each by dividing by 5, actually dividing by 15, we get 1/3. r is 1/3. So we do our check. Is the absolute value of 1/3 less than 1? Yes. Therefore, this converges. That's supposed to be a question mark there. Okay. Therefore, it converges, and we can use our new formula. So let's figure out, what is this summation? As these values get smaller and smaller and smaller, it's going to approach some value. Obviously, it's going to be much bigger than, the 4 we know here added together, or at least a little bit bigger. Well, let's plug in. The infinite sum equals the first term, right? The first term, 405, over 1 minus the common ratio, which is 1/3. So once again, give yourself a common denominator so you can subtract down below. Let's make that 3/3. Minus 1/3 will become 2/3. And again, if I multiply by the reciprocal, we get 405 times 3 divided by 2. So multiply by 3, divide by 2. You could leave it as the fraction. Whoops, I accidentally divided by 2 twice. Let's find the decimal version of the correct one. 607.5. And that seems pretty reasonable for what they gave us. So it's about 607.5. There's our infinite summation. Okay, let's try the same thing for number 2. First, we need the common ratio. So again, r is equal to any term divided by the previous term. So 6 divided by 3, which is 2. So let's do our check. Is the absolute value of 2 less than 1? No. No, it is not. Therefore, this does not converge to a single value. In fact, you can tell this sum is just going to get bigger and bigger and bigger, right, as we keep adding bigger and bigger values. So we'd say this diverges. Now, sometimes it may still ask you to find the infinite sum. It does in this. In this case, we can tell my numbers are just getting bigger and bigger and bigger. Our sum, as this gets infinitely large, is just positive infinity, right? We're just going to get some really big positive value. So the infinite sum is positive infinity. Okay, here's 2 more to try. Again, here, let's figure out r. If I take any term, I'm going to go ahead and take -12. Pick the easiest numbers, right? Divided by the previous term, -3. We end up with +4. Is the absolute value of 4 less than 1? Absolutely not, which means, again, this is going to diverge. It doesn't converge to a nice value, it diverges. And if I looked at this sum, what is it diverging to? We're getting a really, really big negative number, right? If I add all these negative numbers together, we get a really big negative number. So this diverges to negative infinity. So remember, again, we only use this formula if it converges, if it passes our check. So let's try one more here. This one looks a little more complicated, but I can kind of tell my values are getting smaller and smaller, even though some are positive and some are negative, that actually doesn't matter. We're going to look at a crazy looking graph here in a second. But let's figure out r. r equals any term divided by the previous term. So I'm doing 5/4 divided by -5, multiply by the reciprocal, 5/4. Here these 5s would cross cancel, and we end up with -1/4. So r equals -1/4. That's what they're multiplying by each time. Does the absolute value of -1/4, or is that less than 1? Yes. Therefore, this does converge. Even though some numbers are positive and some are negative, it still converges. Kind of hones in on a single value at infinity. And we can still use our formula to find it. So let's plug in our infinite sum equals the first term, -5, over 1 minus our common ratio, which is -1/4. So again, we're going to use a common denominator. Let's make 1 4 out of 4. And because we have minus a negative, we can change that to plus a positive. And we end up with -5 over 5/4. And we multiply by the reciprocal. We get -20 over 5, which is -4. At infinity, the summation here goes to -4. Okay, so what I have here is the graph. If we use the regular sum of the first n terms formula, and we plugged in x as our variable and we graphed it, you can see we get this really weird looking graph going on here. Desmos doesn't even want to try to graph this. But if we look at a table of values, we can see some of these values are shooting around. Some are positive sums, some are negative sums. And what's happening is it's oscillating, or kind of going back and forth between positive and negative sums. And then it starts to get closer and closer and closer to, so we look down here, see sometimes we're at -3.9999, sometimes we're barely above 4, barely below, and it just keeps getting closer and closer and closer to -4. And eventually the calculator even gives up and says, yeah, it's pretty much -4. So even if our summation kind of oscillates on a graph like that, it can still hone in and get closer and closer to a value. Okay, here are a few more. This time they've given it to us in summation notation, or sigma notation. Okay, but remember, we just need the first term and the common ratio. And in fact, in this form, as long as we have the variable -1, which we do for all 4 of these, you can actually think of this as being the first term, and this is the common ratio, right, to the n-1. It's like generating that term. It's exactly the formula that we use to find any individual term in an geometric sequence. So we can actually identify the first term and r directly from the formula here. So here's r. Is the absolute value of 1/2 less than 1? Yes. This does converge. Okay, and if we find our sum, we're going to do our first term, which is 3. It's the infinite sum over 1 minus r, which is 1/2. So find yourself a nice common denominator again. Subtract in the bottom, we get 1/2. And multiply by the reciprocal, which is 2 over 1. We end up, this series, as it goes on forever, converges to exactly 6. At infinity, its summation equals exactly 6. So it just keeps getting closer and closer and closer and closer to 6. Okay, let's try our next one. Once again, we have this kind of same form. We have the first term times r to the n-1. So we can identify our first term as 4, and common ratio is -1/3. So is the absolute value of -1/3 less than 1? Yes. So this also converges. Okay, so let's find its infinite summation. The sum here, as we go to infinity, is our first term over 1 minus the common ratio, -1/3. Once again, we're going to need a common denominator, so 3/3 minus a negative becomes plus a positive. So we end up with 4 over 4/3. And if we multiply by the reciprocal, you'll actually see those 4s will cancel each other out, where we get 12/4. And our answer is 3. This one hones in on exactly 3. So it does converge, and it converges to a summation of 3. Try these last two out for yourself. See if you can find whether they converge or diverge and what their sum is. All right, here we go. So number 7, the answer is yes, it does converge, and its summation is 20 over 6, which reduces to 10/3 or 3 1/3. Number 8, our R value is actually getting bigger. That is a fraction whose value is larger than 1. So no, it does not converge. It, in fact, diverges. So what does it diverge to? Well, think about your series here, right? We're starting with a negative number. And we just keep multiplying by 3/2. We're just going to keep generating more and more negative numbers and adding them up. It's going to diverge to negative infinity. Okay, we'll definitely go over questions and more examples in class. That's it for today.